So we're solving this problem. And when I first started talking to you about approximates, I mentioned that the actual problem statement is really just given by this stuff in black above here. Let me maybe box this in with even a different color. How about yellow? So the problem statement itself is what's in yellow. This is what would be given to you to solve. This is the only information you're usually given for this problem. And maybe, so this is third order, nonlinear ordinary differential equation, third order, and so it needs three conditions to be well posed. So this is all you need to solve the problem. Usually it's solved numerically, but I just wanted to make note of that. So ideally, we would like to use our approximate method to solve the problem just using what's boxed in yellow, and that's it. So it would be a apples to apples comparison with the numerical method. That said, in a way of teaching the method to make things easier for ourselves, in all the videos before this, we've cheated. We used information, extra information we normally would not have, which is a third initial condition that is usually not given with the problem. The second derivative at zero, known also as the shear constant known as kappa, usually written as kappa in papers on the Blasius problem. This value is taken from a numerical solution. We don't really want to do that. We'd rather get this value from the approximate. So that's what we'll talk about today, is how to find the answer to this problem only using the stuff boxed in yellow, how to get kappa, this 0.332 ... from the approximate. So the whole thing is completely independent from a numerical solution. Okay, and there's one other piece, this B right here. B is also something. It's here on the website. They call it beta here, negative 1.720, blah, 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 blah. This is also something we put as an input into our approximate in the last videos. We would like to predict that. So again, so it's completely independent from any numerical solutions. So where did we leave off? So we left off here. This is our approximate boxed in red. And let's run the code here that we ran last time. Right over the last few videos, we've written a MATLAB code, which on here, the circles are the numerical solution to the differential equation. The dashed line here is the power series solution with 12 terms. You can see it diverging. And then using that power series and inputting into our asymptotic approximate, which is boxed in here in red, we get a red curve, which I don't know if you can see that, goes directly through the numerical solution. And as we increase the number of terms, it stays there. It's snapped in, and if anything, the error decreases. Okay, so here's the approximate. Just to remind you what an approximate is it's a function whose expansion on one side is exactly the power series solution to the differential equation. And then it also limits to the correct behavior on another side of the domain. In this case, that would be infinity. So it has the correct infinite behavior. It goes like eta plus b as eta goes to infinity because the last term drops out. And the capital A's are chosen such that the expansion is correct when you expand this about eta equals 0. And it's given by this nice recursion formula that we developed in the last video. Okay, so what we're inputting to this are the initial conditions given in the problem statement, and all coefficients after that. And to do that, we need the stuff that's in green. So the stuff in green right now are inputs to the problem, and they're taken straight from Wikipedia, these two things, kappa, which specifies the second derivative 0, and b. So they come from the numerical solution. We do not want to use those values. We want the approximate to tell us what the values are. So that's the goal of this video. So to talk about how we predict things from the approximate, such as kappa and b, it's important to remember what we're doing here when we solve for these capital A's. All right, so, and I already wrote some stuff here before, so sorry I'm not writing in real time. I wrote this before and then realized that I had to go back and change something. So it's already pre-written here. But to solve for the capital A's, right, what we're doing is we're solving this system of equations right here. Okay, we are matching, making sure that the approximate satisfies not only the initial conditions, but that were given in the problem statement, but all the other higher derivatives evaluated at 0 up to the nth derivative, which gives us n+1 equations, which corresponds to, oops, let me just change this right here. So I will change some stuff here. Okay, so we have n+1 equations, and that allows us to get the n+1 unknowns right here, a0, a1, a2, all the way up to a sub capital N. So that's how we find those. Now, we realized in the last video that there's a quicker way than inverting a matrix. If this was, it is a linear system when you're trying to find just the capital A's. So instead of inverting a matrix, you can develop these recursion relations. So see the last video for that. So now what we can do is get rid of the last coefficient and replace that. So we lose a variable, but we still have n+1 equations. So then we're going to add in a variable. So we want to predict kappa and b. So here's what we're going to do. I'm going to erase this actually. We are going to change what the unknowns are that we want to predict. Keep the same number of equations. Okay, so we're going to make this just go up to a sub n minus 2. So we're getting rid of a sub n minus 1 and a sub n, and we're adding in as unknowns kappa and b. So we still have n+1 unknowns. Effectively, what this means, right, by getting rid of a sub capital N minus 1 and a sub capital N, we're letting those two be 0. So this series over here is now going to, instead of n, it's going to up to n minus 2, right? Because, right, okay, so what this effectively, okay, so we should probably write that down here. So we'll say, maybe we need a different color here. We are sacrificing or getting rid of an and an minus 2 so that we can instead predict kappa and b. Okay. And if you were just using a solver, like say, hey, here's n+1 equations, MATLAB or Mathematica, go ahead and solve it. That'd be the end of the story. You ask it to solve the equations, you get your a0 through an minus 2, kappa and beta, and you're done with it. So that's the story. But there's some slick things we can do to make it so we don't have to force a program to solve the whole system, because this will turn into a nonlinear system by making this replacement, as we'll find out in a little bit. Okay, so we're sacrificing a sub capital N and a sub capital N minus 2 so that we can instead predict kappa and beta. Essentially what this means, right, is that, so in other words, this means that a sub capital N is 0 and a sub n minus 2 is 0, right? They're not in the series anymore, so they are 0. Why is it important to specifically call this out? You might be wondering. Why am I making this obvious statement? The answer is because we have this recursion relation right here, which tells us what a sub capital N is equal to in terms of all the previous a sub capital N's and kappa and beta, and what a sub capital N minus 2 is equal to in terms of all the previous a's and kappa and beta. So we set those two equations equal to 0. We have two equations that will be only functions of kappa and beta. Two equations, two unknowns for kappa and beta. So just pause if you want to think about that, or rewind and watch this a little bit more. I'll try to say this a few other ways though. Here's one way we can think about this. So if we go back a few frames, look at this. When we were doing this the system way, just kind of getting grasps with this whole process, we said, okay, well, let's satisfy the first initial condition, right? That's going to lead to capital A sub 0. In order to satisfy the first initial condition, capital A sub 0 is going to equal 1 over A sub 0 minus B. A sub 0 is 0. So really just negative 1 over B, right? So already the problem is nonlinear in B, and we'll show that nonlinearity is yeah, it's there. B to the negative 1, right? So so already if B is an unknown, we're not solving a system of linear equations anymore, but of nonlinear equations. Okay. Now, since all the equations here are in terms of A sub 0, so A1 depends on A sub 0, A2 depends on A1 and A sub 0, all of the capital A coefficients are going to be functions of B. Okay. And assuming you know the previous coefficients, they'll be functions of B alone and numbers, numerical values, right? Okay, now assume that A2 is not known, because A2 is equal to, I believe, let's go back here, right? Kappa over 2, I believe. So this right here, by the way, is kappa. Okay, so you're going to start getting kappa in your capital A equations as well, because it's dependent on the lowercase a sub 2. And so B and kappa are going to just progress through these equations. And here's what you're going to end up with. You're going to end up with your capital A sub n equation, right? And actually, I'll just kind of modify this a little bit. Right? Because of the recursion relation, your capital A sub n is going to be a function of all the previous A sub n's, B and kappa, and we're setting this equal to 0, right? But all of these are functions of B and kappa, right? And so really you can just rewrite this as A sub n is a function of B and kappa equal to 0, and likewise A sub n minus 1 is a function of B and kappa equal to 0. So you have two equations, two unknowns. So you can use this to find predictions of things in your approximate. So let's do that in MATLAB. Oh, one more thing before we do that. Notice we're saying that we're truncating our series by 2, right? So effectively we're setting A sub n equals 0 and A sub n minus, why did I say n minus 2? You probably called that out, right? And we're wondering why I said that. I meant to say 1. I'm sorry about that. That's a 1. That's a 1. I was just copying from what's above here. Is that a 1? That's a 1. Okay. All right, good. A sub n minus 1. Those are both equal to 0, right? Here's a question for you. Why am I setting them equal to 0 instead of 1 or 2 or 3 or 4? Think about that. Why equal to 0? I want to know what you think about that, and you can put your answer The few people that are watching this video, I know there's just 2 people that have been watching this video. So if you want to think about that and say, you know, why do we choose these things to equal 0 instead of a different number? You can write your answer into the chat, or we can talk about that. But I want you to think about that. I don't want to, I have some answers, or I have some thoughts about that, besides the logic that we went through here, but I'd be interested to know what you think about that, the choice of setting these equal to 0 instead of a different number. Okay, so we have these 2 equations, a sub n equals 0, a sub n minus 1 equals 0. Let's go ahead and modify our code to, instead of enforcing b and kappa, to predict them instead, to make this a completely self-contained method. Okay, so here's our old code. And if you want this code, I know we wrote it from scratch in the last few videos, so maybe you can write it from scratch too if you want, but you just send me an email if you want it. I'll just email it to you so you don't have to rewrite the whole thing. Let's save this as a new file though. Velocity approximate predict stuff. Okay, so the first thing we're going to do is going to comment out this enforced value of b and instead make it symbolic. So sims b. And we also have kappa, sims b and kappa. Remember, this is the numerical solution, so I'm going to leave in a numerical value there for kappa. Okay, so let's turn off the plotting. Since kappa is going to be symbolic, we should probably let the a's be symbolic too, the coefficients of the power series. And I'm going to turn off the plotting here. Okay. And let's just run this to make sure nothing breaks. Okay, so if we look at a of, well, let's see, how many terms do we have? 12, right? So let's crank that down. Why don't we bring this down to 5? And if we look at a of capital N, look at that. It's a function of b, and there should be a kappa in here somewhere too. How about a of capital N minus 1? I see a b in there. That's interesting. So, oh, this is why. I have to set a2 equal to kappa over 2. Okay. 2 is kappa over 2. All right, this time, a of capital N is a function of just being kappa. There we go. All right. So now what we can do is set up a system of equations. So the first equation is going to be a of capital N, and the second equation is going to be a of capital N minus 1. Okay, and then we're going to solve the equations. So we'll say R is the roots of the equations. Solve the equations. And we'll say kappa is equal to double of R dot kappa, because it's a structure, so you have to use the dot thing there, and then we'll change it to a double value, and then I think we can do that. Hopefully we can. We'll find out. And b equals double R dot b. Let's see if this works. That's interesting. Okay, so and again, it's a nonlinear equation. So apparently it gives us 4 roots for each of them, for kappa and for b. Some of them are imaginary. Look at that. Okay, so we want to filter this out. We know that neither b or kappa are imaginary. We know specifically that the b is negative and kappa is positive. So let's call that out. So since b will make this, we'll say we only want the negative, which implies it's going to be real, negative roots, and this one we only want the positive roots. Look at that. Okay, and if we want longer values, we can do format long. So it predicts kappa equaling 0.1255 and beta equals negative 0.608. Now let's see, how does that compare? This is for capital N equals 5. How does that compare with these numbers? They're way off, right? So they're okay, but they're not the correct values. So let's see what the solution looks like when we put them back in. And let's record this. Okay, so let's write this down. So our predictions. So for n is equal to 5, kappa prediction and our b prediction. So kappa, it's saying this is 0.1255, and for b, it's negative 6.089. It's just truncated to that many digits. We can get more digits from MATLAB if we want to. Okay, and so let's actually plot this. So there's a numerical solution. Let's see how well the approximate does if we put these into it. How are we going to do that? Okay, so first of all, here's the approximate code from before. This is only going up to n minus 2, right? Because we're setting a sub n and a sub n minus 1 equal to 0. Also, a sub 0 is a function of b. So we're going to say, for instance, if I type a sub 0, look, it's negative 1 over b, like we said before. We want it to be negative 1 over negative 6.0895. So the eval does that. It says we know what b is, plug in b for that. Same thing for all the a's. So we'll put a b eval there. Maybe we don't have to do it each time, right? So maybe we could instead just say a equals eval a. Let's see if that does anything. Whew. It's not the best, right? Okay, so that's for n equals 5, capital N equals 5. Let's crank it up to 10 and see what we get. Capital N equals 10. It's taking a little while. Well, automatically I see the curves looking better. The red curve is getting, the approximate curve is getting closer to the dots. And for kappa, it's predicting, I guess the only positive root was this one point. Oh, I should change this to be the end column. So for n equals 5, it's that. For n equals 10, we've got 0.3002, which sounds a little bit closer, 0.20000. Okay, these look to be a little bit closer to the values we pulled off of Wikipedia for the numerical solution. And also the curve is getting, the curve looks better, right? It's not aligned up with the numerical solution, but it's getting better. Okay, let's try, and this is completely independent from, this is the approximate on its own, right? Trying to predict all the capital A's and predict all the, and predict B and kappa. Let's try n equals 15 and see what we get. Right, 15 over here. It's taking a little while. Now, one thing that I think might happen here that we didn't run into yet for n equals 5 or n equals 10 is multiple positive roots for kappa, multiple negative roots for b, in which case we want to look for the fastest converging root. So the root that is the closest to the previous one, and also when we look at, say, n equals 20, is the closest, we want to look at the fastest convergence sequence. If we were to plot all the roots versus capital N, they all should be converging to the same thing, is at least my hypothesis. But some of them will converge to the right value faster than others. So we want to look at the fastest converging root. Oh, this is taking a while. Okay. So I'm gonna pause this while this runs. Okay, I wait a little bit and it's still running, so let's kill it. And change, just to speed this up, we're gonna change this to VPA solve. So it's gonna do like some kind of iterative numerical solver to find this. So this is capital N equals 15. Hopefully this will run a little bit faster. Oh, a lot faster. And look at that. It gives us two answers. Oh. And it plotted both answers too. That's interesting. Okay, so really what we'd like to do is to keep doing this for n equals 20, n equals 25, and so on and so on. When we look at that, we'll see that the fastest conversion sequence is going to be the one, I've already done this, that uses the first roots of these two, which also corresponds to the curve that's closer to the numerical solution here. So I'll write down both roots here. Let's say, I'm just going to make a little box here. So we've got, on one hand, there's 0.3263, and then also tells us that a possible root here is 2451. Okay, and over here, there's two possibilities. Okay, so we could have either a negative 1.7717 and negative 2.552. Okay. I'm just going to see if this will run in a reasonable amount of time. If not, then like a cooking show, I'll just pull up the paper where we've done all this already. So n equals 20. Let's see. Yeah, I think that's going to take a little while. So I'll let it run a little bit, but I'll pull up the table from the 2017 paper. In case you want the reference, I guess I'll just pull that up too. It's this one. The DOI number is, I'll just put the reference in the description. I'll just do that. Okay, so we're looking at this table where we made these predictions. Here we go. Okay, so here's this table filled out. And as we looked at the roots, the fastest convergence sequence followed this path here. Okay, and there'd be more, it'd branch out. There'd be more roots as you go down. So at 50 terms, you can see that it converged up to the seventh digit. It it got up to the 7th digit in the numerical solution. But as far as convergence goes, I guess you could probably say it only got up to the 6th digit if you want to look at that digit as converging. And the same thing for B. Although for B, I would say converged up to this digit here, right? Okay, so that's how you would sacrifice higher order terms in your approximate to predict other things, like an unknown initial condition, in this case, the second derivative at 0, kappa, or some asymptotic constant, in this case, capital B. Let's see, we could talk about some more stuff here. One of the things we could talk about is trying to figure out the singularity that's responsible for the divergence of the original power series. Okay, that's another thing that we could look at. But you know what? Why don't we save that for the next video? So the next video we can talk about this might not be as useful from a trying to find a solution standpoint, but it's just an interesting mathematical question. How can you use the approximates? So you could use things like the ratio test to figure out the magnitude or the modulus of the singularity in the complex plane, the distance in this case from 0 in the complex plane, in the complex eta plane. You could figure that out from the ratio test to figure out the modulus of the singularity of the complex plane. But you can use the approximate to identify the location in the complex plane, right? Is it a positive value? Is it a negative value? Is it a completely imaginary value? Or is it somewhere just off in one of the quadrants in the complex eta plane? That's something that we can look at. Perhaps that will be the next video. And then future videos will deal with things like more elaborate problems. And yeah, we've got a lot of stuff to talk about. So I hope this was useful, and have a good morning, afternoon, or evening.